Okay. What I'll do now is to show you a MATLAB code, which will again be uploaded in your respective folders by the NPTEL team. But this MATLAB code will just repeat what I just showed in theory in the previous video. So the idea is very simple. We have the same old problem, the slab, the given data. Now I'm going to show without prior one case, and I'll show you another case with the prior, just like we did in the last video. Okay. So when we try to solve this problem using the offline Bayesian approach, as I said, the offline Bayesian approach means you automatically take samples and you just sample the distribution function there. Okay, so we have only one parameter to solve for. So we are just solving for the heat flux. Now, what we will be trying to do is to estimate the following: the most probable value, which is the peak of the distribution. We also want the mean of the Q distribution, which is given by the expectation, if you remember. So QM will basically be the expectation of Q via the PDF. And of course, we can also find out the variance of the Q distribution. Now, remember, we do not actually have originally the full PDF of Q. So what we can do is we can sample the probability. I'll come back to this point in the next video. And in fact, you can only sample the numerator of the probability. If you remember well, the denominator from the Bayesian is actually missing. So there is a sigma there, there's an integral there, which we do not calculate. Okay, so we do this in steps, as I had written in the previous video. You calculate, you create the original data set, basically give all the given data here. So for example, the physical problem parameters are the thermal conductivity is given, the length is given, the temperature at the right end is given. Now we make some measurements and let's now include that data. If you remember, plus minus 1 is the uncertainty in the thermocouples. This I have written as sigma underscore m, where m stands for measurements. Then the thermocouple locations, X, and the thermocouple measurements, T. Okay, so these are the measurements. Nm is the number of measurements that we have made. Okay. Now, next, we actually create the sampling points. Now, this is where we will differ when we come to the Metropolis Hastings Markov chain Monte Carlo method. In this case, we are simply creating offline sampling points. So we create a sample, a static sample. So if you look at QS, you can see it is simply a linear step between 900 and 1500. We have 11 samples. Okay, so let us just run this code sequentially till now. So I'll just run it just so that we can deal with this step by step. Okay, so if I step this, you can now see what QS is. So the sample QS, in fact, we can write this down, is 900, 960 up till 1500. X, of course, is the locations and T is the temperatures that we have measured so far. Okay. Now, here is the key step. This is basically the Markov chain step, if you want to see it that way. Basically, what we do is we have these ground measurements Ti, but for each Q, so if I step through 1 through NS, for each Q, I will actually generate the actual temperature that we are predicting and find out the differences. So let's do that. So I have just created these matrices. If you remember P1, P2, P3, we'll come back to this point. But if you look at the simulation, so let me write this down here just so that you can see this. Sorry. So we are at the first step. You notice that the actual temperature is these 6 values, whereas our value of Q, we are taking the first sample, we chose Q equal to 900 and that predicted this new set of temperatures, which is what I call the simulated temperature. Now, once you do that, you can actually calculate what the difference between what we predicted and what the truth is. So you can see, so this is The difference, we had seen this in the last video also. Okay. Now, once you have this, you can actually create S. And let me write down S. S is now 6.286. What this represents is the gap or the sum squared between what I predicted, which is T sim, and what the ground truth was. So this is one single number. This is, of course, the sum of the errors, or sum squared of the errors. Now, P1, remember, is the numerator. This is the numerator of the PDF of Q. So this is defined by, if you remember, actually the noise of Q. So minus half times y hat minus y square divided by, now notice the sigma m. Sigma m is the error in each of the thermocouples. So that's what we are doing. P2, let's come here now. P2 is used in order to calculate the mean. Remember, expectation is calculated as whatever value we are interested in this case Q, multiplied by the probability distribution integrated. Okay, so that's what we actually do. So instead of having instead of just having the PDF, you have Q times the PDF. Now I have defined a new quantity, which I call P3A. So let me show that. This I didn't write in the last video, so let me write it down here. Now this is simply Q square. Now why is this useful? We will use the property that expectation of or variance of Q is expectation of Q square minus expectation of Q the whole square. Okay, so this formula you remember. Now, why is this useful? This is useful because when I want to calculate P3, notice this property P3. P3 requires QM. Q1 requires me to actually find out sum of P1, and I don't have it yet. I'll have to run through the whole iteration in order to calculate sum of P1. So I don't want to wait to do that. So instead of that, I will simply sum. I will find out expectation of Q square, then I will subtract expectation of Q the whole square, and that will give me the variance. Okay, so I am using that formula that we had derived earlier on in this course. So, okay, so P1 is just the PDF. This one is the numerator of the mean or the expectation, and this is numerator of expectation of Q square. Okay, so that's what P1, P2, and P3A are. So these are the quantities which we have calculated. Okay, so if we keep on doing that and we continue, let me just stop and I'll run it once more. So if I come here, I have calculated all these quantities. Now you can see, if I write down what P1 is, it's mostly 0 except for a couple of values. There is really, really small values, as you saw while we were calculating it before also. Similarly, you can see P2, only 2 values light up, and you can check P3 also, or P3A, and only 2 values light up here as well. After this, we calculate the denominator, which is the normalizing constant. We can now calculate the posterior PDF, and we can calculate the mean value, and we can calculate the variance. So notice I have calculated the variance as expectation of Q square minus expectation of Q the whole square. Okay, so that's how I have calculated it. And SQ is the standard deviation in Q, which is the square root of the variance. So that's what is calculated. Okay. Now, finally, I plot the PDF that I have calculated, and you can see that here. Okay. So this actually is the PDF. Okay, so you can see point to point, it actually peaks somewhere. If I see this, examine this value, it peaks at around 1260 and you give this sharp PDF. Now notice again, as I had mentioned in the last video, we are not sampling at many points. We are just sampling at these 10, 11 points. Really speaking, the PDF could be something really, really crazy. But what we tend to do is to actually move on and sample it deeper at these points that we have already calculated. Now, we can also see the values of QM that we obtained. I got 1258.7 or 1258.2. I think we got 1258.17 the last time. Let's just check. Okay, yeah, it is 1258.17. We can also check SQ, which is the standard deviation, which is about 10.30. So these can serve as priors for our next iteration. So let's do that. Remember that in the previous case, I had now added all of this information. So now you can see, now we are going to move between 1200 and 1300. We are going to focus on the region where something important is happening. So we'll do that, but we will add a prior. The prior will be 1258.17 as mu, and we had chosen sigma of 0.1 or 10% of mu p. Now there was an error in the previous video that I had shown in the values, which I'll correct right now, not of mu p and sigma p, but while calculating the PDFs, I made a small error. We'll let it be because the purpose of the last video was just to show you the procedure. I'll correct that. The values are not of great importance as far as we are concerned because these are toy problems. We still get reasonable numbers. Okay. Now you notice almost exactly everything else is the same. I have included the priors here. Mu p is 1258.17 and sigma p I have chosen as 10% of mu p. This one should be 1200 to 1300. We have 11 samples. That also remains the same. Everything else is the same except we have the small change. This P1, the basic probability distribution, now depends on two parts. As I had explained in detail in the last video, the first part is the data loss, which is Ti minus T simulation square. And the second part is the loss due to the prior. So in some sense, you can say that A is the data loss and B is prior loss. Okay. So this means how far is my model from the current data? And this asks the question, how far is my model from the prior information that I already have? Okay. So we use all this. So for example, I mean, again, I give this kind of detective story example, but let's say there's a detective story and, you come somewhere, a detective comes and sees a murder. Now, all the data points towards, let us say, somebody that you really know. I mean, you really know some friend or relative of yours and all the data points there. But your prior information is that that person could not do some such thing. Okay. So these two things are in conflict. What prior data says and what current data says. If those two are in a conflict, you have to find out a mean between the two. You have to find out some way of optimizing both these. So remember I said, and I made an error in the previous video. I had missed this factor of 2 in the previous thing. So some of the numbers were wrong in this case with one extra prior. So we have added this prior and there was an error in the previous video. So please do, in case you are going by those numbers, please don't get confused. If you calculate them, you will find them off by a little bit. Anyway, I have corrected that here in the code. Again, T simulation is exactly what we had derived in the last video, minus Q by Kx plus QL by K plus TL. and everything else remains the same. The only thing that changes here is this power of S. This S now becomes A plus B, and A is the data loss and B is the prior loss. We'll look into this multiple loss terms later on when we come to the machine learning portion also, especially when we come to physics informed neural networks. Again, if you see here, the entire code is practically the same. Okay, if I compare the code here, sorry, the code here with the code here, the only extra thing is I have an extra line with A and B defined. Okay, so A is now the data loss and B is now the prior loss, and S is A plus B, and I have put a factor of half because it's common for both of them. And this again remains simply just sigma m square. So include this, everything else remains the same, and we can now happily run this. And you will see we have a much more better informed network here. Let me rerun this just so that. Okay. So now you can see we are getting things in greater detail. Here, of course, the peak is at around 1250. I think I had given 1242 or some such thing, or 1240 in my previous video, but that was because of an error in B. You can also see that the new mean has changed. The new mean is now 1252 instead of the prior, which was 1258. So it has come down a little bit with the new information. And the new standard deviation is around 9.66. So we are a little bit more sure despite the large uncertainty in the previous thing. So now one thing we can try playing with is this sigma p. I can reduce sigma p and say I'm a little bit more certain about this, and I can say sigma p is, let us say, 10. And if I run that, oh, I think I ran it incorrectly. Let me just run that once again. So let's say I gave sigma p of 20. So you can see what happens. If you run sigma p with 20, you are fairly certain about the prior. So the prior gets weighted very highly and it doesn't move very much. It just gets stuck at around 1258 or 1260. So this is one of the reasons why we take 10% of mu p here and give some leeway to how you want to compute the posterior, and then you get a little bit more detailed posterior. So we will take this 10% as a general rule of thumb in creating posterior distributions and using prior distributions. If you use a lower sigma p, you will get sharper posteriors. If you use a higher sigma p, you will get a little bit more elaborate posterior, as you can see here. So here we saw a simple coding example using the offline Bayesian. In the next video, I'll simply give you an idea, though not in too much detail, about the sort of state-of-the-art method, which is Metropolis Hastings Markov chain Monte Carlo. So I'll see you in the next video. Thank you.